Let's take a look at the step response of a series RLC circuit where we have our RLC in series. At time equals 0, we flip the switch or close it, and that means we have a sudden application of a DC source. Okay, so we have a step voltage applied to this RLC circuit, and let's see how this behaves. Let's derive some equations. Okay, so the first thing we want to do is at time t greater than 0, so t greater than 0, we want to, the switch is closed, so that means let's apply KVL around this loop, so around the loop of the circuit for t greater than 0, and then what we'll see is we have L di over dt plus Ri plus V is equal to the voltage source. We know that I is equal to C dV dt. Okay, so we can substitute that into the equation, and then we can rewrite this equation as a second order equation, d squared V over dt squared plus R over L dV dt plus V over LC is equal to Vs over LC. Okay, and then we can further divide this up into a more generic equation based on what we discussed before, and we can actually determine the solution to this equation. So we can have two components as we had in the past for the RC circuit, two components which are going to be the transient response and that's going to be our V sub t of t, and we're going to have the steady state response, and that's going to be our VSS of t. So if we do that, we can come up with a general equation. V of t is equal to Vt of t, or our transient, plus VSS of t. Okay, so this transient response is part of the total response, and then this steady state is also part of the total response. Okay, so if we look at some of the equations we discussed before for the source-free circuit, we can combine them and we can come up with the transient response for the overdamped, the underdamped, and the critically damped. So first, let's scroll up here and let's look at the transient response for the three cases we discussed before, which are the overdamped, critically damped, and underdamped. Okay, so if we do the derivations, we come up with these three equations. So V of t as a function of time is equal to A1 e to the S1t plus A2 e to the S2t, and this is going to be our overdamped response. The second case is going to be our critically damped, so it's the transient response as a function of time, A1 plus A2 times t e to the minus e to the alpha t, and this is going to be our critically damped case. And finally, transient response for the underdamped case is A1 cosine omega dt plus A2 sine omega dt times e to the minus alpha t, and this is going to be under damped. Okay, so however, remember this is for the transient response, so this is the equations for the transient response. We want to come up with the total or the steady state, and then come up with the total response. So let's look at the steady state. Scroll up a little bit. Let's look at the steady state. Steady state response. Okay. And the steady state response is going to be the final value of Vt. So just make a note, final value of V of t. Okay. In the circuit we just showed, the final value of the capacitor voltage is going to be the same as the source voltage. Okay, so we can say, well, our V steady state is going to equal to our final value, it should be infinity, which is going to be the same as Vs, our source value. Alright, so we can just put that on the side there. So now we can rewrite this equation, and remember our total response, so this is going to be our steady state response, and now we can come up with the total response. Total response is just going to be our steady state plus our transient. So we can rewrite these equations. So V of t is equal to our steady state, which is Vs, plus, we're just rewriting the equations from above, A1 e to the S1 t plus A2 e to the S2 t. Okay, and then the second case, and I'll label these again in a second, Vs plus A1 plus A2 t e to the minus alpha t. And then the third state or case is Vs plus A1 cosine omega dt plus A2 sine omega dt e to the minus alpha t, where this is going to be our over damped case. This is going to be our critically damped case, and this is going to be our under damped case. Okay, so we can highlight these, and this is going to be our total response for a step response of a series RLC circuit. Okay, just like we did with the source free, we can find A1 and A2 based on the initial conditions. Okay, so A1 and A2 are going to be obtained from our initial conditions. Okay, and those are going to be from V0 and then dV0 over dt, and we can derive that later on. And if you want a more generic term, we can define another variable. We can put this in terms of x, but let's just stop here and keep this definition as our final definition for our total response for an RLC circuit, starting from this configuration when we put a sudden step response or DC voltage, into the circuit, how does it respond, and we have the transient as well as the steady state response, which is the final value of Vt, and we can define this final set of equations for the 3 different cases as we solve for these problems. Next, we'll talk about the step response for a parallel RLC circuit.